continuing our CCEA GCSE Physics 2016 paper, Unit 2. Question 2 is about light. 2a. The diagram below shows a ray of light passing through a rectangular glass block. What name is given to the bending of the light when it passes from air into glass? Okay, so a nice easy one to start. That's just refraction. Part 2 then. Using a ruler, draw the normal at the point where the light enters the glass. Label the normal with the letter N. Okay, so the light is entering the glass just here. We need a normal. And remember that normal here has its mathematical meaning, which means at 90 degrees too. So we need a line at 90 degrees to the glass block. So very simple, just a line here at 90 degrees where the light enters the glass block. And it says label it N, so be careful, very easy to miss that, like I just did. So always read over the questions and make sure you've answered them completely. Part 3 then, mark clearly on the diagram the angle of incidence in air with the letter I and the angle of refraction in the glass with the letter R. And this is all about measuring angles, and in optics angles are all measured to the normal. That's why we put it on diagrams, because angles are all measured to the normal. So the angle of incidence will be the angle between the incident ray and the normal up here. And the angle of refraction in the glass will be the angle between the refracted ray and the normal just here. So we just mark them, the angle between the incident ray and the normal with an I, and the angle between the refracted ray and the normal with an R. Okay, part 4 then. What causes the light to change direction in the way shown in the diagram when it passes from air into glass? And that's just straight bookwork, remembering from your notes that refraction is caused by a change in the speed of light. In this case, the light is slowing down as it enters the glass. And the mark scheme says you only get 1 if you say change of speed. And the reason is probably here that they've been very specific. We're going air to glass, and so we can say slows down. B1 then. State carefully what is meant by the focal length of a converging lens. So we're asked about specifically the focal length. So this is a distance. And what distance is it? Well, it's the distance between the optical center of the lens and the focal point or principal focus. So the distance from the optical center of the lens to the principal focus, or focal point sometimes, is allowed. Part 2. Describe in detail how you would use the distant object to measure the focal length of a converging lens. In your description you must state the apparatus you would use, describe fully what you would do, state what measurements you must make to find the focal length, and state what you would do to ensure that your measurement of the focal length was as accurate as possible. So, apparatus, well, you need some kind of distant object. The best thing is a window across the room. We need a screen on this side of the room up against the wall or whatever. And we need our converging lens. So what we do is we move the converging lens until we get a sharp image. Then we bring in a meter stick and measure. In particular, we want to measure this distance, the distance from that image to that lens. So we get our distant object across the room, we get a screen up, we move this lens back and forward until we get a nice sharp image. When we get that, we bring in our meter stick and we measure exactly how far it is to the optical center of the lens. And how you would improve the accuracy of that, because that distance is your focal length, is to keep repeating the experiment of trying to get as sharp an image as you can, and that will vary the position of this lens very slightly when you're making adjustments to try and get the sharpest. And then you take a mean of all the values you get for this focal length, and that will give you a more accurate value for the focal length. Part C, the full-scale diagram below shows a converging lens and an object. Each principal focus is marked with an F. Using a ruler, carefully draw two rays on the diagram to find the position of the image. Label the image with the letter I. Okay, so there's a couple of rays we can draw. One of the standard rays here is that a ray through the optical center, which will just keep going. And another one is one that goes through F and then turns parallel after going through the lens. So there's several rays that you can draw, and those would be the main ones. The one going through F that turns and goes parallel, and the one through the optical center that goes straight on. So you can use straight line tool to do these. So that's our first ray. So we need to remember to show a ray through the optical center that goes straight through, a ray through F that turns and goes parallel, and where these meet, that is, they're both coming from the top of the object, so where they meet again is the top of the image, and so it says you need to label your image with an I, and so we need to do that for our image. So we placed arrows on all the rays to show the direction of motion. Next bit, the magnification of an image M is defined by the equation M equals the height of the image over the height of the object. Calculate the magnification of the image in your ray diagram. And this is going to be much easier for you to figure out by measuring the object in the image. It's very difficult for me to do. But it's definitely magnified because the image is definitely bigger than the object. So you would expect this to be an M greater than 1 when you measure them directly. So it's very difficult for me to do anything about this on the iPad. But you measure the height of the image just here. You measure the height of the object just here. You put these numbers in and divide them. So question 4 then, is this image real? Well, it definitely is real because the rays really do cross on the other side of the lens. So yes, the rays really meet and can be formed on a screen. So this is a real image. And that's that.